Okay, here we are. We're starting chapter 5, which is about applications of integration. And we're going to be doing some work with areas and volumes and some other things. But first one is area. We already know integrals can be used for the area of a region between a curve and the x-axis, or more accurately, the net area of a region like that. Now I want to figure out how to use integrals to find the area of a region between two curves. So instead of a curve and a straight line, we've got two curves. The top one here is f of x, and the bottom one here is g of x, so the top one and the bottom one. And we need to find this area S, right? So how are we going to do that? Well, the goal is to do what we did before, divide up the area into a bunch of little rectangles. And then we're going to add up the areas of those little rectangles, and that's an approximation to the area we want. And then we'll take a limit as we use more and more and more rectangles, and that'll get us the exact area. So if you look at one of these rectangles down here below, you see the width of the rectangle is delta x, just like before. And the height of the area, the height of the rectangle is the distance between these two y values, this top y value and this bottom y value. The top y value is from the f curve, so it's f of a particular x value. And the bottom y value is from the g curve, so it's g of a particular x value. So that means the height is f of, we'll go ahead and use xi star for the particular x value, minus g of xi star. Width is delta x, so that means the area of the rectangle is the height. Times the width. And then we add those up, one for each rectangle. So rectangle 1, rectangle 2, rectangle 3, all the way up to the last one, rectangle n, if there are n rectangles. So that's an approximation of the area. Then, of course, if we want the exact area, we have to take a limit of that as the number of rectangles goes to infinity. Okay, and look at that, that's a Riemann sum and a limit. So this is exactly the definition of a definite integral. So that means I can write it as a definite integral. F of x minus g of x is the function. Delta x turns into dx. And I start over there on the left at x equals a, and in on the right with x equals b. So that's the exact area between the curves from x equals a to x equals b. So that means if I divide up my area into vertical rectangles, I have this formula. Now, this is slightly different notation, same idea. So in this notation, A again is the left x value of the region, and B is the right x value of the region. So we have our graph again, and maybe here's two curves. There's A, there's B, and the area we want is in between the two curves, in between those x values. Now, what are yt and yb? Well, they're what f and g were. This is to indicate t for top and b for bottom. So our top curve is yt and our bottom curve is yb. And you subtract top minus bottom y value and integrate that from a to b. Now, if you have a graph to look at, or you are given some information, it can be pretty easy to know what a, b, yt, and yb are, but sometimes you're not. So sometimes you have to find a and b. Often this is when you have two curves and the region in question is between the points of intersection, right? So often A and B are the points of intersection, and you have to set the two y values or functions equal to each other and solve. We'll see an example in a minute. To figure out which function is the top one and which one is the bottom one, you can look at a graph, or you can pick a test x value in the interval between A and B. Sorry, that's in the interval. And then plug it into the two functions. And then the higher result is the top function. Okay, so we'll see an example here in a minute. Okay, so for example, let's find the area enclosed by these two parabolas. Y equals x squared is a regular right side up parabola, and y equals 2x minus x squared is an upside down parabola. So they're probably going to overlap, and that's the area we're looking for, right? So we need to, first of all, find A and B. So we set these two functions equal to each other. X squared equals 2x minus x squared. Move everything to the left. That's 2x squared minus 2x equals 0. Factor out a 2x. And factor out a 2x, and I get x minus 1 remaining. So that means x equals 0 or x equals 1. So this left-hand point is x equals 0, and the right-hand point is x equals 1. Now, I could just look at this little rough picture I've drawn to figure out which curve is on top, but I want to show you this other way. So I need an x value between A and B, so between 0 and 1. I'll pick x equals a half. Put it in my two functions. Y equals x squared. I get 1/2 squared. That's a fourth. Y equals 2x minus x squared. I get 2 times a half minus a half squared. That works out to 3/4. That one's bigger. So this is the top curve. So that means the area I want is the integral from A to B of the top curve minus the bottom curve dx. So in this case, that's the integral from 0 to 1 of 2x minus x squared minus x squared dx. Top curve minus bottom curve. Well, that's pretty easy. 0 to 1 of 2x minus 2x squared. The antiderivative there is x squared minus 2/3 x cubed. And I want to plug in 1 and 0 and subtract. And I think that just works out to 1/3. So the area enclosed by those two parabolas is 1/3 square unit. Okay. Notice there were a few key steps here. I'll point them out again. We had to find the left and right edges of my region, the x values for the left and right edges. We had to figure out which curve was on top. And then we had to do the definite integral to find the area. Okay. I want to show you one more thing here. Instead of vertical rectangle, sometimes we will need horizontal rectangles. Usually this is when you can solve your y equals whatever equation, and it might look nicer to solve for x and get x is a function of y instead of y is a function of x. When this happens, you've got an x is some function of y, and x is some other function of y on the right, you can draw a bunch of little skinny horizontal rectangles with height delta y and width right minus left instead of top minus bottom, and then you get this definite integral. So a now is the bottom y value in the region, b is the top y value in the region, xr is the right hand curve, and xl is the left. And so you do right minus left integral from a equals bottom to b equals top. This is an integral where the variable is y, unlike what we did before where the variable is x. So we'll see some situations like that in class tomorrow. If you are not in class tomorrow, I hope you have a great Thanksgiving, and I'll see you when you get back.